So it's going to be lesson 1.1, free body diagrams and net force. We're going to skip the do now, all right, part of it rather. The first part of the do not say is what is keeping you on the ground right now, and that's going to be your force due to gravity. I think most students would answer that way. They would give me that answer, right? It's something commonplace. You guys are all used to that idea of gravity. I'm just going to move on. If you're watching this video, I highly suggest you watch this YouTube video on the slide yourselves. I can't play it because, well, I'm gonna get copyright strike, and it's not really something I want to happen. All right. So now let's go into pretty much this unit. So this unit is about Newton's laws. And we are going to talk about something called force. And the most basic definition of force is that it's a push or a pull on an object. Now it's measured in newtons, right? That's a unit, just like how the unit for speed was meters per second, the unit for distance or displacement was meters, the unit for force is newtons. Force is a vector, right? You need a direction. It has both magnitude and direction, and the magnitude being the size of an object or the quantity. So you can either push and you're applying a force, or you can pull something and you're also applying a force. And the direction does matter here. Right? So if I push this table, push a chair, I'm applying a force on that chair. I'm pushing on that chair, I'm applying a force. Now, there are many different types of forces. And the first type of force I want to talk about is a force due to gravity, right? F sub g. And this is something really important here, guys. Let me just screenshot this. All right, so we have F G, F sub G. Right, so you have a capital F, right, which signifies force, and then you have lowercase g, which signifies gravity. So F sub G, this G is your subscript. I'm just going to write the G as a smaller addition to that F. It's attached to this F. FG, the nickname for FG is weight, right? So your force due to gravity is your weight. So gravity applies a force on an object, force due to gravity. All right, so what is a normal force? Now, this is the second type of force we're going to be talking about. So we're all apparent about the force due to gravity, right? So the force due to gravity pulls an object down. It pulls an object down, right? So it has the weight. So take, for example, this textbook, this green textbook on this table. You have the weight, your force due to gravity, pulling the object down. Well, what's keeping the object up, right? So if there was only the force due to gravity acting on an object, well, this textbook would fall right through your table. Well, what's happening is that the table is also pushing on this textbook, keeping it up so it doesn't fall through. And we call this the normal force, right? And the reason why you guys are not falling through your chair right now is because, well, the chair pushes up, right? The chair pushes up with a normal force so that the force due to gravity doesn't just pull you straight through that chair and through the ground. So it kind of intuitively, it's kind of hard to think about like an inanimate object pushing on you, but there is a force there, right? There is a force there, and a normal force is something we'll talk about much more in depth later into the school year. But for now, just realize that there is a normal force. There is something called a normal force pushing up on you. Now, this is only true when the two objects, for example, this block and this table, are in contact. Well, if these two objects are not in contact, right, if their surfaces are not touching, well, there is no normal force. The table can't push up on this block because they're not touching, right? And so if they're not touching, if there's no contact, there is no normal force. And your normal force is always perpendicular to your plane of contact, perpendicular being right angles, okay? So right angles. The third type of force is called your force due to friction. So your force due to friction essentially is acting opposite to the direction of motion. If you think about it, what the force through friction actually is that if you think on the microscopic level of two objects, right? Let me just take another screenshot of this. On a very microscopic level of objects, there is something called friction. And friction, if you think about it, on the microscopic level, objects' surfaces are not entirely smooth, right? There are, on the atomic level, the surfaces are jagged. They're jagged, rough, and when these surfaces come into contact with one another, when these surfaces really just start rubbing against one another, well, they generate friction. They cause each other to slow down. Right? They start generating heat. Right? You can readily test this by rubbing your hands together. Right? That heat that's generated is because of friction. Because on a very atomic level, on a very microscopic level, your skin is not entirely smooth. There's a lot of jagged edges, rough surfaces. And so that's where friction comes from. And friction always acts opposite to the direction of motion. So if you're moving to the right, well, your force through friction is acting to the left, right? And vice versa. It's always opposite to your direction of motion. There's something else called applied force. There's something else called applied force. Again, this is the last type of force we'll learn in this class. Your applied force is essentially, well, anything that's a force is being applied on a job, anything that you're applying a force to, let's say you, right, you're pushing on a table, you're applying a force on this table, that's going to be your applied force, right? If I kick a table, well, I'm also applying a force on that table. If a bat hits a baseball, well, that bat is applying a force on that baseball, so that's the applied force, right? And we're going to attribute the applied force to pretty much essentially anything that's applied. So about free body diagrams, when representing motion of objects, right? Let's say for example, a chair, right? So let's say, let's just do that. Let's say for example a chair, right? You're moving a chair. Well, the chair is resting on the ground, right? So I'm just going to draw a box. So there's a force through gravity acting on the box. There's a normal force acting upward, right, from the floor. The floor is pushing the box up, so the box doesn't fall through the ground. Let's say you're pushing on the box, right? So you have someone pushing on the box here, and they're applying a force, right? They're doing an applied force. Well, because the object is moving to the right, right? Because the motion of this object is moving to the right. Well, you have a force through friction acting left, right? Acting opposite to the direction of motion. So that's how we would draw a free body diagram. That's how we would draw a diagram indicating all the forces acting on an object. This is something you guys can watch yourselves, right? I'm not gonna do it for you. Let's go. You can skip this. You can definitely skip that one. So about this one now. So about something called net force. Now, net force isn't really a force in of itself. The net force has a very specific meaning. And the net force is the sum of all your forces acting in one direction. It's the sum. It's your net force, right? So let's take, for example, the simulation. Let's say we add this child to this cart, right? So you're trying to pull this cart to the left or right, and I add this child to the cart, right? What's my sum of all my forces here? Well, the sum of all my forces is 50. So my net force here is 50 newtons to the right. And if I add another child, right? So I add another child here, my sum of all my forces would be 100 newtons. 100 newtons to the right, right? That's my sum. That's my total force, right? Because each child was 50. Well, if I have two children, the sum of my forces is 100. And I add a teenager here, right? So a teenager applies a force of 100 newtons, and so my sum of all my forces is 200. Now, what happens if I add a child to the left? What's the sum of all my forces here? Right? What's the sum of all my forces? Some of you might think, well, the sum of all my forces is 250. But it's not. It's not. The sum of my forces here is 150. Right? And how is this possible? Right? Don't you guys just like, I don't know, do 200 plus 50 is 250? But we learned about this in 0.6. Forces acting to the left are negative, right? Force is a vector, and if you're acting to the left, well, you have a negative force of negative 50 newtons. And so if you were to add both your left and right force, well, you would do 200 plus negative 50 gets you 150 newtons. Right, so that's the sum of all your forces, right? That's your net force. That's your net force. And what would be my net forces if I added another child to the left? Well, my net force would be 100 newtons, right? So my total force here would be 100 newtons. You guys can watch that yourself. And so is my net force here. So let's take a look at the bottom image first, right? Let's look at the bottom image first. So the bottom image, 200, 150. So you have a negative force here, right? So your F net for the bottom image, again, for the bottom image, will be negative 200 plus 150 is equal to negative 50 newtons. And that would be my net force there for the bottom. Let's look at the image on the top right. And so my frictional force here is negative 94, which means I do negative 94 plus 150, and I get 56 newtons. Now, because force is a vector, we need to put the direction here. So we're going to say to the right, 56 newtons to the right. Now, the reason why I didn't put a direction for the other problem is because in physics, the negative sign in of itself is enough to indicate direction. So that the negative sign indicates direction. But the positive sign does not indicate direction. So for us to properly describe force here, we need to put 56 newtons to the right. Right? And we wouldn't say negative 50 newtons to the left. That would be a double negative. All we would say is negative 50 newtons or 50 newtons to the left. Sorry about that. All right. All right, 6C was your net force acting on this block. Your net force acting on this block. If you think about it, right, negative 12 newtons. So your net force is the sum of all your forces. Is equal to negative 12 plus 2, negative 10 newtons. All right, that's that. And you would, again, we will either say negative 10 newtons or 10 newtons to the left. Do not say negative 10 newtons to the left. That's a double negative. You would just say negative 10 newtons or 10 newtons to the left.